All right, we're going to look at some review problems. Some of this will be review, and then some of it will be just some new problems that we didn't get a chance to cover. So, if you feel like you have a good handle on some sections, feel free to just fast forward and follow along on the Desmos and enter any problems that I ask you to enter, and I will go back and look at this later to see who did it to give some extra credit here. Okay, let's take a look at end behavior first. We've done these problems, so this is just some review real quick. So it says, describe the degree and leading coefficient given the shape of the graph. If you want, pause it, try to answer it. I'll go ahead and show you. This is based off that chart that we have, the end behavior chart. But basically, because we've got both of our ends going up, if they're both going in the same direction, it's going to be an even degree. And because they're going up, this means it's going to have a positive leading coefficient. So this would be the correct answer. Okay, next one. Okay, here, one of them is going up and one of them is going down. So right away, we should think that this is an odd degree. So it's going to definitely be one of these two, odd degree. And we talked about on our chart, if we start low and go high, right? It's pretty much, even though it's like does a bunch of stuff, it's in general kind of increasing, right? Going from low to high. So that means if it's increasing like that, it's going to have a positive leading coefficient. So odd degree, positive leading coefficient. Okay, so it'd be something like an x to the fifth power, something with an odd degree, and then you'd have a positive in the front, or like a positive 2 or something like that, not a negative. Okay, taking a look at this one, they're both going in the same direction, so we know it's going to be an even degree. And since it's going down, this is going to have a negative leading coefficient. Good. So this could be, an example could be maybe like, oh, y equals x to the some even degree, so maybe fourth power, but it would have to have a negative out front also. All right, so there was a little end behavior recap. Let's look at writing functions using x-intercepts and something called multiplicity. Now, second period, you guys fully did multiplicity. Sixth period, y'all barely touched on this. So if your sixth period in particular, I would take some notes, make sure you understand this as we go through it. All right, first one's pretty simple. It says write the equation of the function in factored form. Use your x-intercepts. All right, this one's pretty straightforward. I'm going to go ahead, we're going to go quickly through these. So I would locate wherever it's hitting the x-axis here. And remember, they could say use your x-intercepts, but also remember there's other names for x-intercepts. They could call them solutions. They could call them roots. I feel like there's another word for that. Solutions for roots. I know there's another one. I'll let you know if I think about it. Okay, so we've got a root here. Oh, a zero. There we go. Zeros. Could be any of those. Okay, we've got a 0 here at -1. We've got one here at 5 and 6, 7, 8. Looks like that's at 8. So remember, when you put it in factored form, you flip the signs. So yes, technically we have a x equals -1, but if I were to add that 1 to both sides, I'd get an x plus 1 on this side. Okay, so in factored form, it's going to be an x plus 1. All right, flip the signs on all the others. So if it's a +5, I'm going to have an x minus 5. +8, I'm going to have an x minus 8. Boom, that would be factored form. Okay, let's try one more. It says, can you write the equation of this graph based on its x-intercepts? Go ahead and pause this, do it yourself, but I'm going to go ahead and do it right now. So let's see, I've got an intercept here at, let's see, 5, 6, 7, 8, -8. I have one here again, a -1, and then one here at +5. So flip all your signs. So I should see an x plus 8, an x plus 1, and an x minus 5. Okay, good. Let me go back one real quick, make sure I flipped all my signs. Yeah, I did. Okay. Now this is where something kind of weird happens on this one. If you want, try to write this equation in Desmos, but you're going to notice something weird happens because of this x-intercept. Notice this doesn't just like cross the x-axis, it does what I call it bounces on the x-axis. Okay, and then it does cross at a couple points over here. All right, so let's see. That would happen at a -1. This happens at 2. This happens at 4. So to start this off, we can do it like normal, where I could say x plus 1, x minus 2, and x minus 4. But if you actually go and graph that, it's not going to match up with this exactly. And that's because anytime an x-intercept does something like this, where it bounces off the x-axis, it's almost acting like a quadratic here, right? A quadratic is like a y equals x squared, a little parabola, right? So it's like a little mini parabola is happening, which means we need to put a squared on that factor. That squared right there will create this little bounce effect here. Now the other ones are normal. They just cross through the x-axis, so we'll leave them as normal. Technically, they do have like ones right here. We just don't write those. Okay, so this is something called multiplicity. I think I have that on the next slide. Okay, let's go here. Jot down some notes if you need to, but I said zeros and their multiplicity help us determine what the graph looks like at that x-intercept, aka does it cross through the x-axis or does it bounce at the x-axis? Let's look down here. So I think this is the one we just looked at. Yes. So I would say for this factor, I would say -1 is one of our solutions, right? And it has a multiplicity of 2. Okay, I would say 2 is one of our solutions and it has a multiplicity of 1. That's what we would call it because there's technically a 1 exponent out there. And then, of course, this one would be a solution of 4 with a multiplicity of 1 also. Okay, and what you're going to learn here is if you have an even number multiplicity, that is always going to create this bounce effect. If you have an odd number multiplicity, like 1 or even 3 or 5 or 7, those will always cross through the x-axis like normal at those points. Okay, so even numbers like 2, 4, 6, 8, that will do a bounce. Odd numbers like 1, 3, 5, whatever, those will just cross through like normal. Okay, let's see. If you want, go ahead and if you haven't written this down in your notes, do it now. The number of times a factor appears in the factor form of the equation is what we call multiplicity. So if I was taking a look at this, I would say the zeros come from all of the factors here. Technically, the thing that's on the outside of the parentheses, we also set equal to 0, but when we do that and we go 3 equals 0, well, 3 doesn't equal 0, so we kind of just throw that one out, okay? But if we were to set all 3 of these equal to 0 and solve them, we know what would happen. Basically, the sign is going to change on all of them. So I'd get a +1, a -4, and a +5 from all 3 of these. Okay, so the 0 of 1, we would say has a multiplicity of 2 because of this exponent, which means it's going to bounce at the x-axis there. Our 0 of -4, this has our normal multiplicity of 1. If you want, put a 1 right there. And then the last one we would say has a multiplicity of 3. Now, these ones are odd numbers, the 1 and the 3. So those are going to do like a normal thing and they just cross through the x-axis. It's the even ones that are going to make it bounce at the x-axis. If you want to write that down, go for it. If the multiplicity is odd, then the graph crosses at that 0 or x-intercept. And if the multiplicity is even, then the graph bounces at that 0. Again, feel free at any point to pause this, write this down, back it up, whatever you need. Fast forward if you feel like you've got this part, whatever you need here. I'm going to fill this out quickly if you want to pause it and check yourself, but I'm going to do it now. Let's see, I'd get -7. Ooh, careful with this one. Do not put -1 right here. If you set that thing equal to 0 and solve it. Careful, you would subtract 1 first of all, and you'd get 2x equals -1, but then you would have to divide both sides by 2. So we get x equals a -1/2. Okay, so that would be our next 0. And then we'd have a +4. Okay, for the multiplicity, we're just going to look at the exponents. I got a 2, I've got technically a 1, and then I've got a 3. So I'm going to fill that in, 2, 1, and 3. And the effect, if it's an even multiplicity, it's going to bounce at the x-axis at -7. And then these other ones, it's just going to cross because those have odd multiplicity. All right, moving on from that. This just gives you another example. I think we're good there. Let's see. Okay, try this one out. Take a look at it, pause it, see if you can get the right answer. I'll give you a second, and then I'm going to explain it. Okay, so it says, which equation choice could represent the graph shown below? So I have an x-intercept here. I have an x-intercept right here, and it's a weird one, right? That's where it bounces. So I should be thinking this is going to have a squared on it, which all answer choices have a squared somewhere. So just make sure you've got the rest of it filled out correctly. Let's see. So that's going to be, that happens at +1. So in factored form, I'm going to have an x minus 1 squared. So I'm going to look for any of those. Okay, it looks like we found our winner. This is the only one I think that has that, right? The x minus 1 squared. And let's double check it. We have a -3 here, so it should be a +3 in parentheses. Okay, I put random practice problems on the following slides. These are very, very important. Some of these will cover some stuff that we haven't actually had time to cover. So pay attention here. Try to work through these before me if you want, and see if you get them right. Also, put the answers to these in Desmos so that I can go back and see who all completed this to give you a little bit of extra credit. All right, let's see. So this one says two polynomial functions are p of x equals this thing and q of x equals this thing. And then they ask us, what is the product of p and q? I'm going to underline that. Okay, think, what does product mean in math? You should think multiply. So we are simply being asked to take these two polynomials and multiply them together. So what I recommend you do, slap some parentheses around both of them, put them side by side. So I'm going to do that here for the first one. So I've got an x to the third minus 2x, and I'm going to multiply it by x squared plus 4x plus 3. Okay, we have done some multiplication like this in class. In fact, we've done a lot of stuff like this, like FOIL. This one's a little bit more challenging though, because we do have 2 terms times 3 terms over here. A lot of the time we do a binomial times another binomial. So make sure you know how to do one of these. I just know they're going to give you a challenging one like this on. Okay, let's do, I guess you could call it FOIL, but technically it's just distributing. So if we want to solve something like this, we're going to start with this term and we're going to distribute it to everything in that set of parentheses. And then we're going to do the same with the second term, distribute it to everything in that set of parentheses. And when I say distribute, we multiply. All right, let's back it up. Let's do this real quick. If you want to pause it and try it yourself and then check your answer, you can do that. Okay, so first I'm going to start with this x to the third power, and I'm going to multiply it by x squared. Oh, I'm going to use red. Okay, x to the third times x squared. Within multiplication, you should remember that we add our exponents together, so that's going to be x to the fifth power, 3 plus 2. All right, then I've got x to the third times 4x. So that's going to give me a positive 4x to the fourth power. Okay, you've got a 4 here times technically a 1 here to leave you with just a 4. And then x to the third times an x to the 1, add those exponents to get that 4. All right, let's keep going. So then we've got x to the third times 3, which is just a positive 3x to the third. Okay, that takes care of that term. Let's move on to this one. So I have a -2x now to distribute to everything. Let me move this a little bit. There we go. Okay, we got -2x times x squared. That's going to give us a -2x to the third. Remember, you got a 1 on this x plus this 2. Okay, we got a -2x times positive 4x. Negative times positive gives me a negative, and that's going to be 2 times 4 is 8. And then the x times x gives me x squared. All right, and then last one, we got -2x times 3, which is -6x. Okay, that is sort of kind of your answer, but you want to scan this now and check and see if there are any like terms to combine. So We have 1x to the 5th power. Scanning through, there's no other x to the 5th power, so I'm going to bring that down as x to the 5th. All right, let's check the next one. I have a 4x to the 4th. Do I have any other to the 4th? Nope, doesn't look like it, so I'm going to write that out as just plus 4x to the 4th. Okay, next one, we have a 3x to the 3rd. We have another x to the 3rd term right here, so we can combine those. 3x to the 3rd minus 2x to the 3rd would leave us with just 1x to the 3rd positive. So I'm going to put plus 1x to the 3rd. I leave off the 1. Okay, on to the next one. We've got a negative 8x squared and then a minus 6x. There's no other like terms to combine, so I'm just going to bring those down. And that would be it. Can't simplify it any further. Okay, different type of problem here. Let's check this one out. So it says, consider the following two functions. F of x equals 1 half x minus 1, and g of x equals x to the 3rd minus 4x. It says, which of the following represents the approximate solutions to the equation f of x equals g of x? Okay, let's talk about what it means by solutions. We have talked about before, if we're looking at a graph and I say, what are the solutions of the polynomial? Well, we know solutions are where it hits the x-axis. Now, that is only if you have one polynomial graphed. If I said, what are the solutions to where f of x equals g of x. So I created another graph. Let's say it's just a straight line. And I said, what are the solutions to these two equations? In that case, I'm not looking at where they hit the x-axis. I'm looking at where they hit each other. So it would be like 1, 2, 3 solutions for a problem like this. Okay, so what I highly recommend you do if they ask you to solve where two functions equal each other, go to your graphing calculator or to the Desmos calculator, enter these separately, and look at where they intersect. Okay, in fact, I'm going to do that. Let's see, 1 half x minus 1. Let's go graph it. Okay, so I'm going to type it in. This is the Desmos graphing calculator. So y equals 1 half x minus 1. Okay, there's my graph. The second one, if I go back to it, is g of x equals x to the 3rd minus 4x. Let me go enter that. And you know what? You actually don't need to write the y equals. You could just put x to the 3rd. What was it again? Hang on. X to the 3rd minus 4x. Okay. Come out to the side, minus 4x. All right, there's my graph. So if I'm looking for the solutions of where they equal each other, we literally want to look at where they cross each other. And the nice thing about Desmos is if you kind of hover over, it shows you the approximations. And you could give the exact coordinate, but usually what they're looking for is just the x coordinate of each of these. So I could say it happens at approximately negative 2.2, 0.225, and at 2. So when all those x values are those numbers, that's where our solutions are. Okay, then that's how you would list it out, all those decimals. Let's look at another one. They could give it to you like this. So I made up two random crazy looking graphs. I said, use the graph to answer the question. What are the approximate solutions to the equation f of x equals g of x? And they would probably have them labeled as like, this is f of x and this one's g of x. All right, but you're looking at where they equal each other, which means we're looking for where they intersect. And in this case, it would be two of them. Now, it does say what are the approximate solutions because you're going to get a lot of decimals on these types of problems. So looking at that, let's see, that looks like it's approximately at, let's see, about negative 1. So I'm going to say at about x equals negative 1, right? If this is negative 2 right here. And then the other one looks like it is where maybe x equals 1.5, right? If this is 1, this looks like it's about 1.5. There would be my solutions right there. Okay, polynomial division. Let's go through this quickly. If you feel solid on your synthetic division, scroll past this, but there is some important slides later, so don't scroll too far. If you were in my 6th period, we did not get to polynomial division. So if you want to learn it right now, it's actually pretty easy. All right, let's do it. Okay, in the past, this is the kind of division you have done. You've taken a polynomial and divided it by just one term. We don't really need to do that. I just want to show you, you have done this before. This is the new stuff. You have never, up until this point, taken a polynomial and divided it by two terms, right? This is a binomial, and you do it in a very different way. Now, there are two different methods. You can actually do long division to solve this, which we're not going to focus on that because it is quite long. There's kind of a little trick method called synthetic division, and it is surprisingly easy. So I'm going to teach you this method. There's an example of how long division looks on polynomials. It's not the funnest thing ever. Let's learn synthetic division. All right, again, if you're solid on synthetic division, skip past this a little bit. Okay, so to do synthetic division, basically we want to see how many times does this go into that, right? That's division. And what the remainder is in the end is going to be a really important thing for us. So the way we do synthetic division is we set up kind of like a half box first. Now, the thing that you're dividing by over here, this x plus 4, if you actually solve that for x, right, like set it equal to 0 and solve, keep in mind you'd subtract 4 from both sides. So we would say x actually equals a negative 4. So what you're going to put out here is just negative 4. Synthetic division is nice because you drop all the x's and you just do math on the coefficients. Okay, so now what I'm going to write inside right here, inside this bar in this top row, is all the coefficients of the polynomial in the beginning. So I've got a 1, I have a negative 1, I have a negative 27, and I have a negative 28. I'm going to write all those out. 1 with a little space, negative 1, negative 27, negative 28. Okay, this is your setup. Let's go through the process. The first thing you're always going to do is bring this number straight down every time. Okay, so whatever it is, bring it straight down and write it down. Now from here, we're going to go through this same process several times. I'm going to take this number, multiply it by this number, and put the result right here. So negative 4 times 1 gives me negative 4. Okay, so we multiply, and now from here we add straight down. So I'm going to do negative 1 plus negative 4 to give me negative 5. And then you just repeat this process. So then I go back to here, I do negative 4 times negative 5, and I write the result here, which would give me a positive 20. Okay, keep going with it. Now you're going to add straight down. So I've got a negative 27 plus a positive 20 to give me a negative 7. Okay, again, I'm going to do negative 4 times negative 7 to give me a positive 28. And then I add straight down, and here I've got a negative 28 plus a positive 28, which is going to give me 0. And what I want you to do is whatever number you end up with right here, in this case it was 0, box it off in the end like that. That number is always going to be your remainder. Now, your final answer, and I made a little note of this right here. I said, when you write your final answer, drop every term down by 1 degree. So what you're going to do is you're going to take these numbers and you're going to put the x's back into them for your final answer. We took them out to do the division. Now we're going to add them back in for our final answer. And when I say drop it down by a degree, I want you to look at your original. What is the highest exponent you see? Well, it's a 3. So when you put the x back into this, like these are all your coefficients. So I'm going to start by writing 1, and then I'm going to put the x back on it, but I'm going to drop it down a degree. So instead of it being to the 3rd power, it's going to be dropped down to a squared. Okay, so I've got a 1x to the 2nd power. Next up, I'm going to have a minus 5, right? That's going to be my next coefficient. Put my x on there. And it drops down 1 degree. So if this is a squared, it's just going to go down to an x. Okay, from there I have a minus 7. And that's it, right? I have an x squared. I have it dropped down to an x. And then down from there would be no x at all. and I have zero remainder, so that would be my final answer. In fact, I'm gonna I'm gonna get rid of the 1 because you really just don't need unnecessary ones in the end. Okay, there you go. If you want, pause this, try this on your own, and let's set it up. So notice this one I showed you with a division sign. This one I did it as a fraction, but I just want y'all to make a mental note: a fraction is division. Okay, pause this. I'm going to quickly do it. I would have a -3 out here, and I'm going to put all my coefficients inside. So 2, 13, 14, -30, -27. Okay, let's remember the first thing we're always going to do is drop that 2 straight down. Now I'm going to multiply -3 times 2 to give me -6. And then I'm going to add straight down from there, which is going to give me a +7. -3 times 7, I'm going to get -21. Sorry, this is a little messy. Adding straight down gives me a -7. Multiplying again, -3 times -7, that's going to give me a +21. Add straight down again, that's going to give me a -9. And then my last one, -3 times -9, I get a +27. And the same thing happens here. When we add straight down on this one, I get another remainder of 0. Okay, turn this back into a polynomial, add the x's back in. Let's look at where we started. We started with an x to the 4th. So when we put the x back on it, we're going to drop it down to a 3. Okay, so this is going to become a 2x to the 3rd. Next up is a +7, so I'm going to write +7 x squared, drop it down 1, minus 7x, we drop it down 1, and then -9, just our regular constant number there. Again, no remainder. We'll talk about what to do if we do have a remainder. Let's see, I'm going to go on from that a little bit. Let's speed this up a little. So it says, what if the remainder isn't 0? Okay, why don't you go ahead and try this one and see what you get for the remainder. If you want to pause it, I'm going to go ahead and do it right now. So I've got a -5 out here. Coefficients would be a 1, a 1, a -22, and a -1. So 1, 1, -22, -1. Okay, let's bring that 1 down. -5 times 1, I get -5. Adding straight down, 1 plus -5, I get -4. -4 times -5, I get +20. Adding straight down, I get -2. And then -2 times -5, I get a +10. Okay, notice these are not going to cancel out to 0 this time. If I add straight down here, I'm going to get a 9 as my remainder. Let's turn it into our polynomial. So I know this is going to become a 1x to the 2nd power because remember we drop it down 1 from a 3 to a 2. Let's keep going. So then I've got a -4x minus 2. All dropped down a power. Now, we do have a remainder of 9, so this is what we're going to do. I'm not going to spend too much time explaining it, but anytime you have a remainder that's not 0, what that actually means is this is not a factor of that. If you get a remainder of not 0, this is not a factor, okay? Remainders of 0 means this is a factor. So the way we would write it in the end, and I don't think they're going to ask you to do this on your test, but I do think they're going to ask you to know what it means if you have a remainder, and it means this is not a factor, okay? But just to show you, to write a remainder, just put plus and write the remainder over the thing that you're dividing by. So 9 over x plus 5, just like that. Kind of weird looking, but that's how you would write it. Okay, this is an important slide right here. So I am going to reiterate this. It says, what does it mean if you have a remainder of 0 versus a non-zero remainder? So take some notes if you want to. So I put, if you have a remainder of 0 after division, that means the thing you divided by is a factor of the polynomial. If it's not 0, the thing you divided by is not a factor of the polynomial. Okay, you can take a look at these two examples we had here. These are ones that we did. So this one, we got a remainder of 0. And like it says right here, that means that x plus 4 is a factor of the polynomial, remainder 0. And then we talked about how this one, the x plus 5, would not be a factor. All right. What's all this synthetic division stuff about? So it's helpful because it can help us factor and get the roots of higher degree polynomials. It can also help us solve problems like the following. You might see something like this on your test. So take a good look at this one. It says use synthetic division to determine if this is a factor of the polynomial. I said, how could you figure this one out? Give me your thoughts. You can think about it. We're going to go ahead and go through it. But just like we said, if we want to figure out if it is a factor, test out synthetic division and see what you get for your remainder. If your remainder is 0, then bing, 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 yes, it's a factor. If your remainder is anything but 0, that is not a factor. Okay, so let's just test that out right here. So if I draw this out, remember I would put a positive 1 out here. I do not like how I'm writing on top of this, but that's okay. I kind of hate this one because this involves one little thing that I didn't show you. And notice it goes from an x to the third to an x squared, and then there's no x term in between, and then there's a plus 2. You do need to put a placeholder if they're missing a term. I don't think they do this on the test, but in case they do, let's start checking for that. Like if you look at the ones that we did, that has not happened yet, right? Like this one right here went from an x to the third, x squared, x regular number, right? It didn't skip anything. Like it didn't go from an x to the third to an x, nothing like that. Um, yeah, all of these went in like a good decreasing order here, but this one does not. So let's start being mindful of that now. We got an x to the third, an x squared, no x, and then we have a 2. So if there is a missing term, I want you to put a 0 in its place. So I'm going to do a 1 for this one, a 7 for the next one, a 0 for the missing x, and then 2. All right, now we're ready to go. Let's bring the 1 down. 1 times 1 gives me 1. Adding straight down, I get 8. 8 times 1 is 8. 0 plus 8 is 8. 8 times 1 is 8. And then we add 8 plus 2, which is 10. Okay, I don't even need to turn this into a polynomial. The question is, determine if this is a factor. Well, no. We got a remainder of 10, which is not 0, so nope, that is not a factor. Okay, another little thing we have is something called the remainder theorem. So the remainder theorem is similar to what we've been doing, but it states that when a polynomial p of x is divided by a linear polynomial x minus a, then the remainder is equal to what we call p of a. That's a lot of math things. Let's take a look at an example for some clarity here. So this is a type of problem they could give you. They may say, given this polynomial, find f of 1. Now, the way you would probably typically solve this is you would take 1 and you'd go plug it in for all your x's and solve. And if you want, go ahead and do that. But this remainder theorem tells us that if we do synthetic division using this 1, let's do this. Let's put our 1 out here. We don't have to flip the sign because they didn't give it to us as like x minus 1, right? They actually told us it is equal to positive 1. So I can put a positive 1 out here. Let's check and see if we need any 0 placeholders. I've got a x to the 5th, 4th, 3rd, 2nd, 1, and then normal numbers. So we're good. We will write our coefficients as 3, 2, 4, 3, 2, and negative 3. Okay, so again, if you want to find f of 1, you could go plug 1s in for everything and see what you get. In fact, if you do that, you can kind of do it mentally, right? Like 1 to the 5th power is just 1 times 3. It's just going to give you 3 for this term. And then same thing here, you'll get a 2 for this one, a 4 for this one, a 3 for this, 2 times 1 is just 2, and then minus 3. Add those up really quick. 3, 4, 5, 6, 7, 8, 9, 14, 13, 12, 11. I believe we get 11. If I did that right, we're going to find out soon. I did that very quick. Now, if you do synthetic division on this, your remainder is going to be your answer. That is the remainder theorem. If you do f of a number, the remainder will give you that answer. So let's try it. Bring down my 3. 1 times 3 is 3. 3 plus 2 is 5. 5 times 1 is 5. 4 plus 5 is 9. 1 times 9 is 9. Add them, we get 12. 12 times 1 is 12. We get 14. 14 times 1 is 14. And look at that. Add them together, we get 11 for my remainder. So you have a new way of solving these things. If they ask you to find f of some number, yeah, go ahead and plug it in if you want, or do the synthetic division here, and whatever your remainder is, that is your answer. So answer would be 11. F of 1 equals 11, you could say. Okay, using the remainder theorem. Let's see. That's basically exactly what we just said. If you want to take notes on it, you can. Go ahead and try one. If you want to pause this, try it on your own. Use the remainder theorem to evaluate f of -3. Again, if you want to go plug in -3s for all the x's and solve, go for it. I don't recommend it. It's tricky when you have negatives in parentheses and you're squaring them and cubing them and all that. Let's do it with our new remainder theorem and synthetic division. Okay, I'm going to put a -3 out here. I'm going to check for placeholders. I have an x to the third, an x squared, an x, and regular numbers, so we don't have to put zeros anywhere. So I'm going to jot all these down. 3, 6, -4, 1. All right, I'm going to bring down my 3. 3 times -3, -9. Add them together, that's a -3. Multiply, -3 times -3, I get +9. Add straight down, I get 5. Multiply 5 times -3, I get -15. And adding straight down, I get -14. And in this case, that is my answer. F of -3 should equal -14 if we did it right. Now I'm going very fast, so if I made a mistake, it's possible. Let me know. Let me know in the comments here if I made a mistake if you're on Desmos. Okay, really good, like think about little question. This is actually our last one we're gonna do. So this is definitely some type of question I could see them giving you, where it's like a more like you have to think through it than solve it. So it tells us q of x is a polynomial. If q of 7 equals 0, which statement must be true? Once you think about that, that follows the remainder theorem we just did. So we don't know what the polynomial is, but we know when we did 7 on it, right? Like if we set this up, we did 7, we ended up with a remainder of 0. Think about what that has to mean. We know that something with a remainder of 0 means we have a factor. So I would cross out the ones that say not a factor, because if you get a remainder of 0, you definitely have a factor. So which one is it? Is it x plus 7 is a factor or x minus 7 is a factor? Well, we know when we have the number out here versus in factored form, they're always flipped signs. So if I put that in factored form, it's going to be an x minus 7. This would be our correct answer. Okay, past that, I think that's probably some good review material. I know that was kind of quick. There are some things from Unit 1 that we never got to. We just have not had enough time this year. You know, we started super late in the year. If you want to learn some of those, I think there could be a couple questions on your IA over this. I recommend going to Khan Academy, or you can go to YouTube and searching arithmetic sequences. Yeah, it looks like arithmetic. They call them arithmetic, and something called geometric sequences. It is possible they'll ask you on your tests about recursive formulas and explicit formulas. So if you want to look at videos that talk about those, you can do that as well. So that's just some extra. If you want to be super duper prepared for this thing, search that. Okay, make sure you're entering this stuff on Desmos. I'm sending that link on Canvas along with the link to this video. And if I can see that you have worked on this and you've worked through these problems and submitted some answers, then you're going to get some extra credit. All right, good luck, guys. We will talk next week.